Okay, let's look at how elements bond and a little bit about oxidation and reduction. So we're going to look mainly at two types of bonding, covalent bonding and ionic bonding. Covalent is usually between nonmetals and we share valence electrons, and ionic bonding is usually between metals and nonmetals and we have a transfer of electrons. And that's where we'll talk about the redox. Okay, so valence electrons, they occupy the outermost orbitals of an atom. Those orbitals have these designations S and P, so outermost orbitals. In the main groups, again, as we talked about with the periodic table, the group number gives us information about the valence electrons. So group 1A, 1 valence electron, group 2A, 2 valence electrons, 3A, 3 valence electrons, 4A, 4 valence electrons, so on and so forth. Okay. So here, my alkali metals, remember those were group 1A, so they have 1 valence electron, 1, 1, 1. Group 2A, those alkaline earth metals, 2 valence electrons, 2, 2, 2. Okay, halogens, group 7A, so 7 valence electrons, so 2 plus 5 gives me 7, 2 plus 5 gives me 7. All right, and then our noble gases. So helium only has an s orbital, so it can only fit 2 electrons. So it's fine and full at 2 electrons. But the rest of the noble gases, they need those 8 electrons to be full. 2 plus 6 gives me 8. 2 plus 6 gives me 8. So what atoms are trying to do is they're trying to obtain what we call an octet. Oct means 8. So a full valence shell of 8 electrons. They want to be like the noble gases. Okay, so basically they're going to lose, gain, or share electrons to attain that filled outer shell, usually of 8, but sometimes of 2, like hydrogen, element number 1, also only has an s orbital. Helium only has the s orbital, so we can only fit 2 electrons there. So those guys are perfectly happy with a valence shell of 2 electrons. Okay. So when I look at something like water, hydrogen and oxygen, they're both nonmetals. So they like to bond covalently. Co together, valent, talking about the valence electrons. So they share. So oxygen has 6. It wants 2 more. Hydrogen has 1. It only wants 1 more. So what happens is they will pair up and share electrons. When we're covalently bonded, each element in a covalent bond considers all the electrons belonging to them. And so oxygen, we have 1, 2, 3, 4, 5, 6, 7, 8. Perfectly happy. Hydrogen, 1, 2, boom, happy. Hydrogen, 1, 2, boom, perfectly happy. Okay. Now, when these bonding situations occur, things happen such that we get various different ratios giving us different compounds, but the key thing is they have to be in a whole number ratio. I cannot bond half of an atom or a quarter of an atom. Okay, I can look at these numbers here, these percentages, and turn them into masses, and then do a division with the masses on the periodic table. And here, let me show you. This first one, the carbon monoxide. 1 carbon, 1 oxide, carbon monoxide. Okay, all right. I'm going to take the 57.1 divided by 16. I'm going to get 3.56. I'm going to take the 42.9 divided by 12.01 to get 3.57. Okay, those are decimal numbers. We don't want decimal numbers. We want whole numbers. So I'm going to divide by the lowest number. It's a 3.56, but they're basically the same. Gives me 1. Gives me 1. There's my 1-to-1 ratio. I have 1 oxygen, 1 carbon. I get my carbon monoxide. I can do the same thing for the carbon dioxide. I can take that 72.7 divided by my 16. I get 4.54. I take my 27.3 divided by 12.01. This time I'm going to get 2.275. So these numbers are not the same. We're not going to get that 1-to-1. But if we divide by the lowest number, divided by 2.28, divided by 2.28, I'm going to get 2. I'm going to get 1. So I'm going to get 2 oxygens and 1 carbon, which is where I get that CO2 for carbon dioxide. So everything is in whole number ratios. When we form our ions, okay, cations, positive. So we have lost electrons for cations. This makes sense because protons are positive, electrons are negative. We're only moving electrons around. So I have my fixed number of protons in my atom. If I get rid of electrons, now I have more protons than I do electrons, which means I have an excess of positive charge. For anions, the opposite is true. I'm gaining in electrons. I still have my fixed number of protons. But now if I put in negative charges, I have more negatives than I do positives, so it is negative. Okay? Our cations are going to tend to be our metals. Our anions are going to be our nonmetals. Okay, so our metals have fewer valence electrons. Our nonmetals have more valence electrons. So we're trying to get to 8. At the end of every period, our noble gas has a full valence shell. So what our atoms are trying to do is have a valence shell that looks like a noble gas. So let's think about this. If I have something like sodium with 1 valence electron, what's going to be easier, losing 1 valence electron and looking like the previous filled noble gas, or gaining 7 more and trying to get up to the upcoming noble gas? Well, it's easier to lose 1. Same thing with magnesium. It's got 2 valence electrons. It's easier to lose 2 than it is to gain 6. Same thing if I have 3 valence electrons, like aluminum. It's going to be easier for aluminum to lose 3 than to gain 5. When I get to 5 valence electrons, like nitrogen, well, nitrogen, let's see, is it easier to lose 5 or gain 3? Well, now we're past the halfway mark. It's actually easier to gain 3 than it is to get rid of 5. My group 6A, like oxygen, it's easier to gain 2 than to get rid of 6. My halogens, it's easier to gain 1 than to get rid of 7. Okay? What I show here is dealing with the electrons. Now, if I have a full chemical equation, I don't show electrons. Electrons only show up in what we call half reactions. Okay, so these guys I have on here are all half reactions. Half reactions let me account for the movement of the electrons. Okay, now when I write any chemical equation, it has to be balanced, whether it's a full chemical equation or it's a half reaction. So if I take a look at my sodium here, let's see if it's balanced on both sides. Okay, so my neutral sodium atom has no charge to it. My sodium cation has a +1 charge, and my electron has a -1. +1 and -1 gives me 0. Does 0 equal 0? Yes, it is balanced. If I look over here at my sulfur, I have a sulfur plus 2 electrons yields a sulfide anion. So my neutral sulfur is 0. My 2 electrons -2. My sulfide ion -2. Does -2 equal -2? Yes. So our half reactions are indeed balanced. Now, when we talk about half reactions, that is redox or oxidation reduction chemistry. So we'll talk about a little bit more about that in just a moment. I just want to show you when we look at our metals, again, they like to lose electrons and form cations, and our nonmetals like to gain electrons and form anions. Okay, so this oxidation and reduction. So what's happening is one species is what we call oxidized, and the other species is reduced. You can't have one process without the other. I am an electrochemist. This was what I did all the time. Well, I did fancier versions of this, but I worked with this sort of a situation. So I mentioned earlier I did redox dependent hydrogen bonding. So it depended on the oxidation or reduction state that something was in. So if something loses electrons, we say it is oxidized and it gets more positive. If it gains electrons, it is reduced and it gets more negative. Okay? We have this cool mnemonic, oil rig. We use it all the time in my lab. Oxidation is loss, reduction is gain. And what we're referring to is loss and gain of electrons. Okay, so let's take a look at a couple half reactions and put a whole thing together so you can see how it works. Let's say I'm forming magnesium chloride. Okay, magnesium chloride has a formula that looks like this. It's an ionic compound. So we're going to form magnesium ions from magnesium metal and chloride ions from non-metal chlorine gas. Okay, so we have a couple of half reactions. So magnesium is going to look like this. 2 valence electrons, so it forms a +2. Okay. All right, and then my chlorine okay, so I have 2 chlorines. So remember, chlorine is in group 7A. So each chlorine would lose, or which chlorine would gain 1 electron. Chlorine exists naturally as a diatomic, so I have to account for both chlorines, which is why I get 2 electrons and 2 chlorides there. Okay, so when I look at my overall reaction here, let's see here. Again, when I put an overall reaction together, the electrons don't show up. So these are my half reactions. So oxidation's a loss of electrons, reduction's a gain of electrons. So my magnesium's oxidized. My chlorine's reduced, okay? Oxidation, my electrons are always products. Reduction, my electrons are always reactants. Okay, so when I put a full chemical equation together, I don't want electrons in the final equation. So anything that's the same on both sides gets canceled out. So here is my reaction arrow. So here I have 2 electrons on my product side and 2 electrons on my reactant side. They're going to cancel out. So now what I'm going to get is my magnesium and my chlorine give me magnesium chloride, and the electrons don't show up in that final reaction. So when we bond, we do have 3 major bonding models. Okay, we have ionic bonding, covalent bonding, and metallic bonding. So ionic bonding, again, metal, non-metal. Covalent bonding, non-metal, non-metal, and then our metallic bonding, it's really interesting. It's what's called an electron C. So all the valence electrons, if I have a sample of a metal, are what we call delocalized. They're floating throughout the entire sample of that metal, which is really cool because we know that metals are good conductors. And why are metals good conductors? Well, because of this electron C. In order to conduct electricity, we need mobile charge. So if I have a bunch of electrons that are free flowing in my sample of metal, I have mobile charge. Therefore, I have really good conductivity of electricity. This is also why things like tap water will conduct electricity. If I have dissolved stuff in my water, it means I have, instead of an ionic compound that's neutral, I have the ions will disassociate and flow throughout the sample of water. And so I have ions floating around, so I have mobile charge, so I conduct electricity. This is why your hairdryer tells you on it, don't stand in water while you're using your hairdryer because you could electrocute yourself. Okay, so those are our 3 major bonding models. All right, so chemical bonds, we have these forces of attraction holding things together. Ionic bonds, we get that full redox reaction where we have electrons transferred from one species to the other. So we get a cation, we get an anion, we get these electrostatic forces that hold everything together because opposites attract. Covalent bonds, again, covalent, we are sharing valence electrons. Ionic bonds, metal, non-metal, or metal and what we call a polyatomic anion. So we have some nonmetals that are bonded together to form an ion, and then covalent bonds, we get nonmetals bonded together. Okay, and so our ionic bonds, loss and gain of electrons. So oxidation and reduction. Oxidation is loss, reduction is gain. And then our covalent bonds, we are sharing electrons. All right, and so our ionic bonds, we say that those are formula units, and our covalent bonds, those are discrete molecules. Okay, so when I form compounds, okay, they want to be neutral. So ionic compounds have to be in that ratio to give me something neutral. So when we put it together, how did I get to CaBr2? Okay, well, calcium's at a +2, and I need some number of those. Bromine's at a -1, and some number of those has to equal 0. So +2 and -1, the common number of both of those is going to divide into is 2. So 2 times 1 gives me 2. 1 times 2. So then I get a +2 and a -2, which give me the 0. So then there's my 1 calcium and 2 bromines. Okay, my aluminum oxide down here. Aluminum's at a +3. I have some number of them. My oxygen's at a -2, some number of them. I have to equal 0. So 2 and 3, the common number both of those divide into is 6. So 3 times 2 gives me 6. 2 times 3 gives me 6. +3 times 2 gives me +6. And then -2 times 3 gives me -6. So there's my neutral compound. And so I have 2 aluminums and 3 oxygens. And so our formulas are written with the number of each atom subscripted. We don't need to have a 1 if we only have 1 of something. All right, so let's try a few of these here. Okay, so lithium and oxygen. So lithium is in group 1A, so it's going to form a +1. Okay, and usually we just put a plus, right? Oxygen is in group 6A, so it's going to form a -2. Okay, so to try to put it all together, I'm going to have a +1, and it has to equal 0. So the common number these will both work with is 2. So I'll have 2 of the +1 charge and 1 of the -2 charge. So 2 of the +1 charge, so that's 2 lithiums, and 1 of the -2 charge, 1 oxygen, so Li2O. Okay, magnesium and chlorine. Magnesium is in group 2A, so we're going to get that +2 ion. Chlorine is group 7A, so we're going to get that -1. Okay, so I'm going to get a +2 times some number, plus a -1 times some number has to equal 0. Again, 2 and 1, the common number is 2. So I'll need 1 of the +2 charge and 2 of the -1 charge. So the +2 charge is the magnesium, so I only need 1 of those. The -1 charge is the chlorine, so I need 2 of those. Okay. Aluminum and nitrogen. Aluminum is group 3A, so it's going to have 3 valence electrons. So we'll get a +3. Nitrogen is group 5A. It has 5 valence electrons, so we need to add 3. So we'll get a -3. This one's easy. +3 times some number plus -3 times some number +3 -3. They already cancel each other out, so I only need 1 of each of those. Okay. Now this last one, this one's a little bit weird. I have this Roman numeral there. So there's transition metals. Okay, these guys are weird. Transition metals don't just form predictable ions. Transition metals can form a lot of different types of ions. So when we're outside the main group, when we get to that center section with the transition metals, to know what ion they form, we have to have a Roman numeral. that Roman numeral is going to tell us the charge of the ion. So vanadium 5 means it's a vanadium with a +5 charge. Okay, sulfur, main group, predictable, it's in group 6A, so we need 2 more electrons, so it's going to make a -2. Okay, so we're going to get a +5 charge times some number plus a -2 charge times some number needs to give us our neutral species. Okay, so 5 and 2, the number they both divide into is 10. So 5 times 2 gives me 10, and 2 times 5 gives me 10. All right, so I need 2 of the +5 charge. Okay, and I need 5 of the -2 charge. Okay, so I get V2S5 there. All right, so most things we can look at those group numbers to figure out our charge, but those transition metals, you have to have that Roman numeral that tells you what the charge is, because they can form lots of different things. Like copper can do a +1 or a +2. Iron +2 or +3. So I have to have a Roman numeral that tells me what my particular charge state is there, or my oxidation state. Okay, and then just to finish off here, when we think about all these different elements and that conductivity stuff, so the easier it is for electrons to move around, the more conductive it is. So this is why all these metals are great when we deal with making batteries or wires or parts of our cell phones. So metals, good conductors. So think about those bonding models. That electron C, mobile charge, and then tap water. Okay, we have those ions that dissociate. And so we've got, again, on the periodic table, those metals, the non-metals, and then the metalloids, the semi-metals. These guys are really interesting, and the semiconductor industry exploits these really significantly because they have these bridging properties between the metal and non-metal. We can do a lot of really interesting things with them because of that. So that is our bonding.